Take a look at these two responses. Same model, same data, same question, but the output quality, night and day. One is vague, generic, reads like a first draft. The other is precise, perfectly formatted, cites its sources, and sounds like it was written by someone who actually works at the company. So what changed? Not the model, not the data, not the infrastructure, the prompt. And I'm going to let you in on something that I've seen over and over again working with enterprise clients. Teams will spend 6 months building a RAG pipeline, fine-tuning models, deploying complex infrastructure, the whole 9 yards. And then they realize that a well-engineered system prompt with 5 good examples would have gotten them 90% of the way there. Prompt engineering is the most underinvested, highest ROI lever in enterprise AI. And I mean that. It's the thing that costs nothing, takes the least time, and often makes the biggest difference. In this episode, we are covering everything that happens inside the context window. System prompts, few-shot learning, chain of thought reasoning, prompt caching that can cut your bill by 90%, semantic caching, and conversation memory management. No GPUs, no training, no new infrastructure. Just the techniques that make every other architecture in this series work better. Alright, let's start by breaking down what a production-grade enterprise prompt actually looks like. Because it's not just a paragraph of instructions, it's a layered architecture, and each layer has a specific job. The system prompt is your control plane. This is where you define who the model is, how it behaves, and what rules it absolutely must follow. In enterprise deployments, this typically runs 500 to 5,000 tokens of carefully crafted instructions. And here's how I structure it for clients. Start with the role definition and be specific. Do not use anything like you are a helpful assistant. That's useless. More like you are a senior financial analyst at Acme Corp who specializes in quarterly earnings analysis. You report to the VP of Finance and your analysis is read by the executive team. The more precise the role, the more consistent and appropriate the outputs. The model actually calibrates its language, depth, and assumptions based on this. Next, behavioral constraints. Always cite the specific data source for any claim. Never speculate about future performance unless explicitly asked. If the available data is insufficient to answer the question, state exactly what additional information you would need rather than guessing. These are your guardrails at the prompt level. Think of them as the rules of engagement. Then consider about defining output format specification. I cannot stress this enough. Be explicit about format. Respond using this JSON schema. Or structure your analysis with these specific section headers. Or use XML tags to separate your reasoning from your conclusion. Explicit format definitions eliminate about 80% of output parsing failures. The model is really good at following format instructions. You just have to actually give them. And finally, domain knowledge injection. This is where you put the stuff the model needs to know to be effective. Key terminology definitions, abbreviations specific to your company, business rules. When the user refers to Tier 1 accounts, this means accounts with annual recurring revenue over 500K. Without this, the model is guessing at what your internal jargon means. Okay, this is the technique that most teams massively underuse, and it frustrates me because it's so effective. Few short examples. Instead of describing what you want, you show the model exactly what good looks like. You include 3 to 10 gold standard input-output pairs right there in the prompt. And your example should cover 3 scenarios. The typical case, what 70% of queries look like. The edge case, ambiguous inputs, incomplete data, boundary conditions. And the refusal case, when the model should say, I don't have enough information to answer that. Or, this should be escalated to a human. Now, here's the thing that most people don't realize about few short examples. Your examples define the model's behavior more powerfully than your instructions. Let me say that again because it's that important. If your instructions say be concise, but all 5 of your examples are 500-word responses, guess what the model is going to do? It's going to write 500-word responses. The examples always win over the instructions. For classification tasks, going from 0 shot to 5 good examples can jump your accuracy from 70% to 95% plus with 0 training. For extraction tasks, pulling structured data from unstructured text, good examples are the single biggest quality lever you have. And this is where prompt engineering meets system architecture. At runtime, you programmatically inject data that's relevant to the specific request. User profile and preferences, recent interaction history, retrieved documents from your RAG system, live data from API calls, session state from the conversation. All of it gets assembled into the prompt before it goes to the model. And here's what's changed. With modern context windows exceeding 200,000 tokens on Claude, you can fit an enormous amount of relevant information in a single prompt. Entire customer histories, full policy documents, product catalogs. Things that used to require a database lookup followed by careful summarization can now just go directly in the context. But think of your context window as a budget. You need to allocate tokens strategically. Fixed system prompt and examples, that's 2,000 to 5,000 tokens. This part doesn't change between requests, which is why it's perfect for caching, and we'll get to that. Dynamic context, that's 10,000 to 100,000 plus tokens depending on your task. This is your RAG results, user data, whatever is specific to this request. Conversation history varies based on your memory strategy, which we'll cover later. User query, typically 50 to 500 tokens. And then you need to reserve generation headroom, 2,000 to 8,000 tokens for the model's actual response. Don't fill your context window to the brim. Leave room for the model to think and respond. Alright, beyond the basic prompt structure, there are some advanced techniques that can dramatically improve the quality of your outputs, especially for complex enterprise tasks. This one's simple, but incredibly powerful. Instead of asking the model to just give you an answer, ask it to show its work. Before giving your final answer, reason through this step by step. First, identify all the relevant data points. Then, apply the calculation methodology. Check your work for logical consistency. Finally, state your conclusion with a confidence level. For multi-step analytical tasks, financial analysis, compliance evaluation, technical troubleshooting, chain of thought can literally double your accuracy. And the reason is fascinating. The model catches its own errors during the reasoning process. It'll start down one path, realize the numbers don't add up, and self-correct. Without chain of thought, it just commits to its first instinct. And on Claude specifically, you can use extended thinking, which lets the model reason internally before responding. It's like giving the model scratch paper. It thinks deeply, works through the problem, and then gives you a clean, confident answer. For complex analytical tasks, this is a game changer. REACT stands for reasoning plus action. And it's the pattern that interleaves thinking with doing. The model thinks about what information it needs. I need to find this customer's subscription tier to answer their billing question. It takes an action. Let me query the customer database for account ID 12345. It observes the result. Okay, they're on the enterprise tier with annual billing. And then it thinks again about what to do next. This back and forth, thought, action, observation, thought, action, is actually the prompting pattern that powers Bedrock agents under the hood. When your agent is deciding which tool to call and how to interpret the results, it's running a REACT loop. Understanding this pattern helps you write better tool descriptions and agent instructions. For high-stakes decisions, here's a technique that's expensive but incredibly effective. Generate multiple responses with the temperature turned up above zero, so you get variation. Then look at the answers. If 4 out of 5 reasoning paths reach the same conclusion, your confidence should be much higher than if you just generated a single response. It costs 5x per query, so you wouldn't use this for everything. But for decisions with real financial impact, compliance reviews, risk assessments, situations where being wrong is really expensive, absolutely worth it. Okay, this is one of my favorite patterns for complex enterprise workflows. Instead of trying to do everything in a single prompt, you break the task into a sequence of simpler prompts. Each one does one thing well, and its output feeds the next one. Here's an example. Document analysis pipeline. Prompt 1. Extract all financial figures and their context from this document. It returns structured data. Clean extraction, nothing else. Prompt 2. Given these financial figures, calculate year-over-year changes and identify anomalies. Takes the structured data from step 1, does the analysis, Prompt 3. Given this analysis, generate an executive summary with key findings and 3 recommendations. Takes the analysis, produces the deliverable. Each step is independently testable and debuggable. If the extraction is wrong, you fix the extraction prompt. If the analysis is right, but the summary is bad, you fix the summary prompt. And here's a bonus. You can use different models for different steps. A fast, cheap model like Haiku for extraction. A more powerful model for analysis. Optimize cost and quality independently at each stage. On AWS, implement this with step functions orchestrating Lambda functions, each calling Bedrock with a different prompt template. Beautiful, clean, maintainable. 2 more techniques that I use on every enterprise project. XML tag prompting. Wrap your analysis in these tags. Analysis, confidence level, sources cited, follow us pose question. Claude responds exceptionally well to XML structured prompts. The tags create natural boundaries that make the outputs consistent and trivially parsable. Your downstream code can just grab the content of each tag. No regex nightmares. JSON mode with schemas. Provide the exact JSON schema you expect. Respond with a JSON object matching the schema. Verdict as a string. Confidence as a number between 0 and 1. Evidence as an array of strings. Recommended actors of an array of strings. Clean, structured, machine-readable output every time. Now let's talk money. Because enterprise LLM systems at scale, the token bills add up fast. And here's what most people don't realize. The majority of those tokens are repeated on every single request. Your system prompt, your few short examples, your static context, all of that is identical across thousands of requests per day. And you're paying full price for all those repeated tokens every time. That's like printing the same textbook from scratch for every student in the class. Prompt caching fixes this. And the numbers are kind of ridiculous. On Amazon Bedrock with Claude, here's what happens. Your first request sends the full prompt. System instructions, examples, static context, user query, the whole thing. Bedrock looks at the static portion, everything that doesn't change between requests, and caches it. The KV cache, the intermediate computation, it's all stored. Now the next request comes in with the same static prefix, but a different user query. Bedrock recognizes the cached prefix, skips reprocessing those tokens entirely, and only processes the new stuff. You pay a tiny cache read cost instead of full input token pricing. And the model responds faster because it doesn't have to reprocess thousands of tokens it's already seen. The numbers. On Claude via Bedrock, cached input tokens cost 90% less than fresh input tokens. And latency for the cached portion drops by over 80%. Let me do the math on a real scenario because it's compelling. You've got a system prompt with 3000 tokens. Few short examples with 2000 tokens. That's 5000 tokens repeated on every request. At 1000 requests per day, that's 5 million input tokens per day just for the static prefix without caching. 5 million tokens times $0.003 per 1000 tokens equals $15 per day. Just for the stuff that's exactly the same every time. With caching, 5 million tokens times $0.0003 per 1000 tokens equals $1.50 per day, plus a one-time cache write cost that's negligible. That's $13.5 per day saved on just the static prefix. Sound small? Scale it. At 100,000 requests per day, you're saving $1,350 daily. That's over $490,000 annually on one optimization that you can implement in about 10 lines of code. Now, to make caching work, you need to be intentional about how you structure your prompts. The cache matches from the beginning of the prompt forward. Everything before the first difference between two requests gets cached. So structure your prompts with caching in mind. Static prefix first. System prompt, role definition, behavior and rules, few short examples. This stuff never changes. Put it at the very beginning. Semi-static context next. User profile, account details, reference data that changes per user, but stays the same within a session. Dynamic content last. Retrieved documents, conversation history, the current query. This changes every request. This ordering maximizes your cache hit rate. If you put dynamic content in the middle of your prompt, everything after it becomes uncacheable. On Bedrock, you enable caching by adding cache control markers in your messages. You mark the boundary where your static prefix ends. Bedrock handles the rest: cache creation, storage, invalidation, billing. No infrastructure to manage, no TTL logic to write. It's baked right into the API call. So prompt caching saves on repeated prefixes. But what about repeated questions? That's where semantic caching comes in. Think about it this way. User A asks, "What's the return policy for electronics?" at 9 a.m. User B asks, "How do I return an electronic item?" at 9:15 a.m. Semantically, same question. Different words, but they want the exact same answer. Without semantic caching, you call the LLM twice. Same answer, twice the cost, twice the latency. With semantic caching, you embed each incoming query, search for cached responses with high semantic similarity, and if you find a match above your threshold, you return the cached response instantly. No LLM call. Milliseconds instead of seconds. The architecture is straightforward. Query comes in, embed it with your embedding model. Search your cache. This can be Elasticache with a vector plugin, Amazon MemoryDB for Redis, or even a lightweight OpenSearch index dedicated to caching. If the similarity to a previous query exceeds your threshold, return the cached response. If not, call the LLM, generate the response, and cache it with its query embedding for next time. In practice, this reduces LLM calls by 20 to 60% for enterprise systems with recurring query patterns. Customer support, internal help desks, FAQ-heavy domains, any system where people tend to ask the same questions in slightly different ways. Now, before you get too excited, let me give you the caveats, because this can go wrong if you're not careful. Similarity threshold. Set it high, like 0.95 minimum. What's the return policy for electronics? And what's the warranty policy for electronics? Those are semantically close, but they have completely different answers. A threshold that's too low will serve the wrong cached response. That's worse than no caching at all. Personalized responses. If the answer depends on who's asking, their account status, their permissions, their preferences, then caching the response for one user and serving it to another is a data leak. Don't cache personalized answers unless your cache key includes the user context. Cache invalidation. When your source data changes, your cached answers are stale. Implement TTL-based expiration. Cache responses for hours or days, not forever. And if you update a critical document in your knowledge base, have a mechanism to flush related cached responses. All right, the last major topic for this episode, and it's one that trips up a lot of teams: conversation memory. Enterprise AI systems aren't single turn. Users have extended conversations. They ask follow-up questions. They reference things they said 15 messages ago. Agents execute multi-step workflows that span dozens of interactions. And every single one of those messages takes up tokens in your context window. After 20 turns of a detailed technical support conversation, you might have 50,000 tokens of history sitting in your context. After 50 turns, you're bumping up against your context limit. And now, there's no room left for your system prompt, your RAG results, or even a decent response. You need a memory management strategy. So let me walk you through the options. The simplest approach. Keep the last n messages. Drop everything older. Predictable token usage. Easy to implement. The downside is obvious. If the user set up important context in message 3, like I'm migrating a 50 terabyte Oracle database to Aurora Postgres, and you're now on message 25, that context is gone. The model has no idea about the migration. The user gets frustrated repeating themselves. Best for short, transactional interactions where each turn is relatively self-contained. This is my go-to recommendation for most enterprise use cases. Periodically, you take the older messages and summarize them into a compact paragraph. Recent messages stay verbatim. So instead of 50 full messages, you've got something like previous conversation summary. The user is a data engineer migrating a 50 TB Oracle database to Aurora PostgreSQL. They've completed the schema conversion phase and are now troubleshooting data type mapping issues, specifically with CLOB columns and Oracle-specific date formats. We've identified 3 potential solutions and they chose option 2. Then the last 5 to 10 messages are kept word for word. The summary captures the essential context. The recent messages maintain the exact nuance of the current discussion thread. Implementation tip: use a smaller, faster model to generate summaries. Claude Haiku is perfect for this. It's fast, cheap, and genuinely good at summarization. Run the summarization whenever your conversation exceeds a token threshold. Like when history hits 30,000 tokens, summarize everything except the last 10 messages down to a 500 token summary. Let me talk about an entirely different approach. Instead of keeping or summarizing the conversation text, you extract key entities and facts and store them in a structured format. In this example, username, account ID, current issues, technologies involved, decisions made, and action items would be key entities. At each turn, you inject the relevant entities into the prompt, not the full conversation. This is extremely token efficient, but you lose narrative flow. The model doesn't remember how the conversation got to where it is, just the key facts. Best for agent workflows where specific data points matter more than conversational context. And then there's the fancy approach. Embed every message in the conversation. When the user sends a new message, retrieve the most semantically relevant past messages, not just the most recent ones. So if the user says, actually, let's go back to what we discussed about the CLOB columns, the system retrieves those specific earlier messages even if they were 30 turns ago. This handles the "what did we talk about earlier" pattern gracefully. This approach works best for complex, long-running conversations where users reference earlier topics non-linearly. Quick note on the managed side. Bedrock Agent supports session-based memory natively. Within a session, the agent maintains full conversation history. For cross-session memory, remembering a user across completely different conversations, you can integrate with DynamoDB to persist user context and inject it into the agent's prompt when a new session starts. For custom implementations, the pattern is Conversation Manager in Lambda, Message Store in DynamoDB, Summary generation on a schedule or a token threshold, and relevant history injection into each Bedrock API call. Alright, let me tie everything in this episode together. Because all of these techniques aren't separate things, they are layers in a single architecture. Your production prompt architecture looks like this. Cade static prefix, system prompt, role definition, rules, few short examples. Prompt caching saves you 90% on these tokens. Set it up once, save money forever. Dynamic context injection, RAG results, user profile, session state. Assembled, fresh per request. Memory layer, conversation history managed by whatever strategy fits your use case. Sliding window for simple stuff, summary buffer for most enterprise conversations, vector memory for the complex, non-linear ones. Semantic cache check. Before you even call the LLM, check if you've answered this question before. If yes, return instantly. If no, proceed. Generation with structured output. Chain of thought reasoning for complex tasks. XML tags or JSON schemas for clean, parsable output. This is the context window architecture that underlies every pattern in the series. Whether you're doing RAG, tool use, or running agents, the quality of what's inside that context window determines the quality of what comes out. In part 4, we're going deep on tool use, function calling, and MCP, the Model Context Protocol. This is where the LLM stops being a text generator and starts being an actor in your enterprise systems. Live database queries, API calls, code execution, and the emerging open standard that's changing how AI systems integrate with basically everything. See you in part 4.